Hello and welcome. In this problem, we'd like to calculate the adiabatic flame temperature of methane burning with theoretical amount of air. That means methane and air are coming at 100 kPa and 290 Kelvin, 98 Kelvin, into a combustion chamber, and which is totally insulated. That's why Q dot out or Q dot in equals 0, and the resulting temperature is known as the adiabatic flame temperature. So we are asked to find that assuming variable specific heat. That is, we are supposed to use the NIG model. Okay, so let's go and set up the reaction. First, we launch an appropriate test step. We follow the open specific branch, combustion and chemical equilibrium, and we'll use the NIG mixture model because Cp and Cv can be a function of temperature. Balancing the reaction is easy because it's a simple reaction. So we add 1 kilomole of methane to our reaction chamber. Fuel is already selected here. This is the fuel. And theoretical combustion with air is given here. We execute this action and the theoretical reaction is shown. Now we calculate the fuel state, which is 100 kPa and 298 Kelvin. Mass is automatically picked up. 1 kilomole of fuel is 16 kg. So it's a oxidizer. Look, the state 2 is kind of logged with oxidizer, state 3 with products, etc. in non-premixed combustion. So we enter the pressure and temperature of the oxidizer, and for product, state 3 is products. We know the pressure, but we don't know the temperature. That's what is desired. That's the adiabatic flame temperature. So you go to the device panel and see if you can take advantage of the energy equation to find that. So in the energy equation, in the device panel, we set up the reaction chamber. State 1 is fuel, state 2 is oxidizer, and let's say state 3 is products, and we'll leave the fourth port blocked as is shown here. There is no work transfer and there is no heat transfer. So energy solution should produce J at the exit. Let's calculate and go back to the state panel. And yes, J3 has been found, as you can see. Now you can finish the calculation by clicking the calculate button. And as you can see, the adiabatic flame temperature is found as 2328 Kelvin. Of course, the device panel is updated too. We could go to the device panel and update to find the entropy generation during combustion. Anyways, so let's go and do the second part of the problem, that what if we have deficient air, that is only 90% of air is available. So let's write down this answer, 23228. We'll be able to show that this is the highest temperature you can ever obtain in a theoretical combustion of methane with air. So let's go set up the reaction this time with not theoretical reaction. So all we go, fuel is already chosen, with theoretical combustion with excess or deficient air, right? So 2B is our correct action. And look, lambda is a variable that shows up now. Lambda is the percent theoretical air used. So instead of 100 will make it theoretical air. So 90% or 0.9 value for lambda means there is only deficient air available and some fuel will be left over at the end of the reaction. The reaction is completely balanced. Now, nothing changes in the state panel, state 1, 2, and 3. I mean, no input changes. So all you have to do is to do a super calculate to update the panels. And on state 3, we'll find the adiabatic flame temperature. It is 2307 as opposed to 2329 Kelvin or something that we got. Likewise, if you want to now repeat the calculation for 110%, so we can go back and say balance the reaction again with excess or deficient air, and lambda will be 110% this time, execute. Because there is excess air, some oxygen will be left over at the end of the reaction. all we do now is click the super calculate button and come back to the state panel to pick up the temperature T2191. So as you can see, the adiabatic flame temperature is the highest at the theoretical reaction when lambda equals 100%.